No. Okay. So I made a video where I went, or yesterday? Yeah, yesterday we had you guys. I was gone. So I made a video and I picked out some problems that I thought would be good exemplars. One of them was this problem 39 or 37 from 3.9. So this is a related rates problem. So I made a boo-boo when I was doing this because, well, I had a sick daughter and I was distracted and, you just goobered something here. So I blew the derivative here, that this should be 0 and this should be plus. And then that's 0 and that's plus. And then this number is just wrong. It's supposed to be 396.396, which makes a heck of a lot more sense because that 13 meters per minute is like, that's really ripping. That's a big changing triangle there. So just FYI, if you were looking at the video and you're like, that's not for why, huh? Yes, Mr. Cooling did it. He goofed it. But I picked a bunch of problems here and I just kind of, the idea was like for you to like listen to the problem or look at the problem or whatever, pause the video, try to work on it until you finished or you got stuck, watch what I did, and as soon as you saw a mistake in your work, to pause, fix your mistake, and then try to finish, and then restart the video after you refinished or got a little further till you got stuck again, and just kind of like work through the video or work through the problem with me. If you watch the video, I think that's the introduction that kind of I describe how you should be using this. So if you didn't get a chance to do that, I recommend doing that because I picked these problems for a reason. I think they're good ones that I think would be helpful to look at before the exam. Anyway, so there's a boo-boo on that one. And then there's one at the end that I didn't get to because it felt like by the time I had finished recording, it was like 50 minutes worth of video. And I'm like, well, if you're following along, and then we're talking about this optimization problem, which is no piece of cake here, that you certainly would have been done with class. So I was like, well, maybe I just stop here because I wasn't really watching how long I'd taken to do the other ones. I just picked some good ones. Anyway, so I'd like to do this one, and then you guys can hit me up with whatever. Does that sound okay? So this is 30 from 4.7. I don't think I assigned this one, but I thought it was a good one. Mostly because the algebra doesn't get terrible in it.
Isn't this the one that we did in class?
No, it was we did 31.
Inside of a
sphere, yes. And we had that stupid radical equation that we had to solve. This one, the solving is considerably easier, which is why I like this problem so much better, because it's like the same idea, but like massively less inconvenient. So I'd like to kind of approach this the same way that we would have in the video. So why don't you guys get out something, either your scrap sheet of paper, your notebook, or your tablet, or wherever you want to do it, and just try to work through this problem here a little bit. We'll take 10 or so minutes, and then I'll kind of start walking through it with you guys. And I'll even do this for you. So we have a right cylinder inscribed in a cone with height yada yada and base yada yada. So here's a picture I found on the internet of this situation. The only change is that we have to call the picture, they labeled that cap H and cap R. So I'll just change the problem so that it's cap H and cap R, and then I'll give you this picture. And let you pick away at this, and I'll touch base in a couple of minutes and see if we're still working or if you need some help moving forward, and we can move forward a little bit, and you tell me what you need. But I thought this was a good one. Mostly because the algebra parts weren't super annoying. And then you guys can fire away at whatever. You guys don't have to whisper either. Like, it's not like this is top secret or I'm going to grade this or anything, or it's a test, you know, like. We're just having a conversation or whatever, you know.
Given the nature of this problem.
Most calculus problems, having an eraser is usually helpful, right? It's hard to do it perfect the first time. I don't know. I think they have a designated person at the door that punches you in the face if you try to do that, though.
Oh, okay.
They see a pen in your hand, you just, you know, like right in the nose real quick. Nothing else happens other than that, other than you have to like try to take the exam with a concussion or whatever, like a broken nose, some toilet paper stuffed in your nostril to keep the blood from stopping. Keep the blood from stopping. That's not what I meant. To stop the blood from dripping on your paper. Keep it in there. And I'm joking about, obviously, the person punching you in the face. It's just, we're just making jokes here, trying to get a chuckle. Teagues.
What's the volume for a cylinder?
Yeah, what is the volume for a cylinder? Yeah, just the area of the base times the height. So in this picture, we'd say pi r squared h. So the little r was the radius of the cylinder, and the small h is the height of the cylinder.
Perfect. Thank you.
Yep. Now notice that those are both variables, right?
Yeah.
Oh shoot. You know what that could oh. No, isn't that like a related triangles thing?
Similar triangles, yeah, is what you'd want to use in this for sure.
That's what I used.
Well, that's a good thing.
Good ear.
So let's just say.
All right.
Yeah.
So you have that guy,
I'm not even messing with it.
and you have this guy.
I'm not even finding. So I'm on the right track. That's a good sign.
That's great, guys. So I'd call that piece Y.
Yeah, where it's like yeah.
Segment CD.
Okay. wait, so just to confirm, like pretty much also all the measurements on the actual cone, so like the cap H and the cap R, those are constant.
Yes, excellent observation, Blake.
And then
the dimensions of the cone are constant. Those are not changing. Cap R and cap H are constants because we're trying to fit a cylinder inside of a cone of fixed radius and height.
Do we want to get H in terms of? Do you want R in terms of H? Can you change R in terms of H?
Or you could write both R and H in terms of Y, right? Which is probably what I think is the most obvious thing to do. Right? Because I can just observe that cap H is Y plus little h. And I can just make little h cap H minus Y. So, I mean, it doesn't matter what you use as your variable. You could do this in terms of R. You could do it in terms of, I should say, little r. You could do it in terms of little h. Or you can do it in terms of y. It doesn't really matter. All of those are doable. In fact, when I looked at the answer key in the text, I think they used everything in terms of little r, which would be fine. You could do that also. But to me, it just seems more obvious to write it all in terms of this y.
Wait, y was the longer leg of this small triangle, right? Or what was y?
The distance from the top of the cylinder to the top of the cone.
Oh.
This is when we get to derived.
So I just dropped in my value for r and little h into the formula above. So now I have an equation in terms of one variable. That one variable is y, which is not a dimension of the cone or of the cylinder at all, but that's okay. It's still a variable. It still describes the situation.
Yeah.
I can rewrite y in terms of little h and little r, or I can use that to find the dimensions for little h and little r, so it's fine. It's good enough. Everybody's okay?
And okay, and so another confirmation. So when we actually, so I'm going to make this the magical step and derive this. And so it's pi is like it's a constant. And so is r over h. So you can do like you can bring the pi out, do the chain rule.
Oh, Blake, don't do that.
Oh.
Let's just simplify this thing.
Can you do that?
So I'll do the squaring, and then I'll just distribute it all through.
Is this like what happened?
Right?
Yeah.
Like, and then if you want to differentiate this, that's a piece of cake, because what kind of function is that? Here, I'll make it more obvious.
Oh, you distributed.
Yeah, man. What kind of function is that? That's just a regular.
That's just a regular.
Old,
those are all constants.
Yeah, it's just a regular old polynomial. Yeah. Look at how wonderful that is to differentiate now. Isn't that much easier than like talking about chaining and producting and all that nonsense? Like, get out of town. Man, let's do that.
And can you you can pull out the yeah.
Well, this part doesn't matter when I do the derivative, right?
Right. Well, it's like our coefficient.
Yeah, it's just a coefficient. So it's just going to be 2 pi r squared h times y minus 3 pi r squared h squared y squared. Done. Easy. 2-second derivative. It's like the easiest derivative you'll ever have to do, right? Now, there was one step in here that we have kind of skated past.
We need to find the domain.
Yeah. What's the domain for this going to be? I'm going to look at this guy right here because I think it'll be easiest to kind of tell. So we're talking about y, which is a measurement, right? So what can I say immediately? Yeah, got to be bigger than 0, right?
Yes.
And if I look at this piece, what else can I say about y?
It's got to be smaller than h.
Smaller than h. And here's even the best part about choosing y. Notice, is y in the denominator any place?
No.
No. So I've closed interval, which is nice because that means the testing my derivative at the end is that much easier. Everybody cool?
Yes.
Great. All right. So if I look at my derivative here, yeah, Tegan.
Sorry, I'm just a little confused on how it can equal h as well.
Well, if it equals h,
It would just be 0.
yeah, the volume is 0. You're just going to have like a straight line.
Okay, yeah.
Like, it means the radius is 0,
Okay.
right? Which is fine, like whatever. It's going to be an easy check at the end. Okay. So we have our function in terms of a single variable. We have the domain for that function. And we have the derivative. What do we do next? Kind of. We want to find the critical values of the derivative, which are where the derivative doesn't exist and where it's equal to 0. Now, what kind of function is our derivative? Polynomial. So the derivative exists everywhere.
Well, yeah.
So all we really need is the zeros, yeah. But I do need to, we do need to make sure that we're at least saying that we have to look for where the derivative doesn't exist because, well, not every problem, the derivative exists everywhere, right? So that's what we're solving. How do you solve that?
Wait.
What's up?
Can you like pull out you can pull out the pi r squared 8 over h? Like, can't you just divide and get rid of it?
I mean, let's just regular old factor this thing. It's just a polynomial set equal to 0. What's the factoring that we're going to do? Greatest common factor, right? So we'll just take out a pi r squared over h times y.
Wait. Did I like miss this? I feel like I missed something. Because why aren't both of those h squared up at the first equation?
So when I distribute it here, the h cancels with one of the h's in the denominator, but it doesn't on another one, right? So one's h and one's h squared.
Okay.
Is that okay? And look at how easy this solving is, right? It's just the greatest common factor. Now that it's factored, I can just use the zero product property to set each of those factors equal to 0. Well, that first one is super easy. Constant times y equal to 0. Well, just y has to be 0. This other one, I'm going to subtract the 2 over and then multiply by the reciprocal. So 2/3 h. That's some better algebra than that. What was it, 31 that we were trying to do with that horrific square root one in there? Yikes, or Rooney. Yeah. So now to figure out what the maximum is, we'll just do the closed interval test. So what values do we need to check? We need to check the endpoints and our critical values. Now, one of our critical values is also an endpoint, but we do need to check the other endpoint of our domain. Now, that's pretty trivially easy. We observed right away that when y was 0, the volume was 0, and when y was h, the volume was 0. So right away we know that this guy has to be the maximum. And now I'm just going to plug it in to evaluate what we had. So I think I'm going to go ahead and plug in this one that I've starred. Yeah, what's up, John?
Never mind.
Yeah, I mean, it doesn't really matter where you plug it into. I just think this one feels easier. Because I see...
Whether it's the original...
Or the one that we did the derivative to.
Right.
Yeah, whether you take the original or simplified, it's going to give you the same result. It doesn't matter. This just looked easier to me to do kind of in my head. So here, the h's cancel, swell. And over here, h minus 2/3 h is just 1/3 h. All right? I don't even mean common denominators or nothing. Like, that's rad. So let's see. I got my pi still. And then I squared 2/3. That gives me 4/9. And I square the r. That's r squared. And then I have times h over 3. So what do I get here? I get 4 pi r squared h over 27. So that's my maximum volume. And if I wanted the dimensions for that cylinder, what would I do? Well, what was little h again? Yeah, it was cap h minus y, which is just h over 3. And we'll say and then r was, or little r was, so when I plug that in, I get 2/3 h times r over h, which is just 2/3 r. So those are my dimensions for my cylinder. What do you guys think? Now this would be an example of like one of these 10-point multi-part questions, right? And it would not just be what you read. I would have broken this up into a bunch of parts where I asked you to do some of these steps that we did. You know, like I probably would give you the picture and ask you to label. You know, like the labels, I wouldn't have included like this stuff in there. So like one point might have just been like adding labels to the picture from the words, you know. This piece, which was probably the most difficult part, getting to here, would probably be a show question, like show that the volume of the cylinder can be represented in a single variable as this. And what's nice about me wording it that way?
You know what single variable.
Yeah, you have the equation. So like you have the correct equation for the volume. So in the next step, when I ask you to differentiate, it's not a problem because you have the correct, you can still keep going because you have the correct volume, right? So next part might be like asking for the derivative, okay? The next part might be like solving or finding the critical values. The next part might be what values do I actually have to do I have to check to find the maximum?
Wait, one just quick reminder, how did you find, like, like for the closed interval test, why did you choose H?
So if you go back and you look here, the closed interval test says you need to check the critical points and the endpoints on the closed interval.
Oh.
So the endpoints on our closed interval were 0 and H. So I had to check those as well as my critical values. Now, if this was an open interval, what would you have to do differently?
The first derivative of the second.
Excellent. Yes, the first derivative or second derivative test. My suggestion in this sort of situation would probably be I would opt for the second derivative test because the derivative was so easy to do
Yeah.
that I would just be like, yeah, I'm just going to do that and hope I can show it's negative. Always. If I'm looking for a maximum, or show that it's positive always if I was looking for a minimum.
In the second derivative.
Yeah. Yeah.
Wait, you're showing it's positive always to prove it's a maximum, not just positive.
Well, but if it's, what I would be hoping for is not to have to plug in. I'd hope for something that I was just like, oh yeah, all that's left are constants that are based on measurements, which has to be positive, or a negative, like constants are based, you know what I mean? Like I'd hope that all the variables just dropped off and it would be like an acceleration sort of situation where it's like the second derivative is just a number everywhere.
Yeah.
Or something that's like clearly always positive or always negative is usually what I'm hoping for on these kind of optimization problems. Now I could always do a first derivative test where I pick values, but like that stinks considering all of these are just in terms of letters, right? To do a first derivative test here, I'd have to pick, like 1/3 H and like, 4/5 H or something, which stinks to plug in to show that like, that those are negative and positive. Like that's just a lot of simplifying. It's really stinky. I'd much rather deal with the second derivative test there and only have to plug one thing in.
Right.
You know what I mean? Particularly when I already know what the thing is, right? Like I'd be plugging in 2/3 H, which is a little less stinky. If there's even a variable left. Ideally, there's no variable left, and it's like, oh, this thing is just always the thing that I need it to be, positive or negative. You know what I mean? That's kind of best case scenario. That would happen a fair bit on these kind of optimization problems. Does everybody feel okay on that one? So again, the goal on the exam is, are we doing every problem? No, we're collecting points, right? So you're doing the stuff that you know how to do and that you know how to do fast. Because you want to collect as many points as you can as quickly as you can so that you can get to the stuff it's like, yeah, this is going to be time consuming, but maybe I think I know what to do. That should be done second. And the stuff that's like, maybe I know how to do this, that should be done last. Right? Amanda?
Will you kind of like have them in like sections like 4 point like something, or is it like everywhere?
It is all mixed up.
That's
You know why I chose to do that though?
funny.
That's how the AP exam is going to look. It's half of the problem is selecting what you need to do this. Now, the other nice thing about this though, about me doing that, is that you can do stuff any way you want, right? Like if you catch a limit problem, you don't need to use like the techniques from chapter 2. You could use L'Hopital on it, right? You don't have to do a derivative using the definition of derivative if I don't ask you to. You can use, all of your shortcuts, the product rule, chain rule, etc. Like you do that, right? Like, so it's about using what's appropriate. Like you don't have to use the first derivative test or second derivative test. You can just use whichever one you want, right? You don't have to use one versus the other. Do what you want. You know what I mean? Aside from, unless it's like specifically ask you in the directions, but I'm not going to do that unless it's like a problem that I want you to use calculus on and not your calculator. Like a Newton's method problem. It's like find an approximate solution for this equation using Newton's method, because ordinarily you just type in your calculator and graph D and find the 0 or whatever, right? Like I don't want you to do that. I want you to do the calculus thing. And I would say that, again, like you probably will see a use the definition of the derivative to find some derivative on there. Like that's a standard AP Calc exam question where that'll pop up. At some point, you'll have to use the definition of the derivative, almost assuredly. So that's, again, like that's something I would say is fair game, but not every derivative problem is going to be like that. That would be like one standalone version. Okay. What else do you guys want to talk about? Did you guys have things you wanted to talk about? I'm happy to do some other stuff. I just felt like I wanted to talk about that one because I thought that was a good exemplar of an optimization problem where it didn't get too ugly, right? Like nowhere in there did the algebra get just like horrific. But it was like just the right amount of sneaky. You know what I mean? A little sneaky without being too sneaky. That's what Mr. Kulik was looking for. Or just any kind of exam stuff, whatever. I'm happy to just do stuff or talk about stuff. Again, on the exam info page, if you didn't notice, I went and pulled example questions of stuff. For the sake of your father, don't try to do every single problem I listed. They're just like, I just grabbed blocks of problems that were like, yeah, you should be able to do stuff that looks like this, which I thought would be pretty appropriate. Blake?
I haven't personally looked over these questions.
Sure.
These specific questions yet.
That's okay.
So could you do just like one of like the extreme value theorem questions? Like I don't really care which one. I don't like understand that in the mean value theorem. I don't really understand like what it is.
Okay.
I watched the videos. I did the homework.
Yeah.
It kind of the info went right over my head.
Sure. So let's just do this real quick, and I'll grab the. Where did you go? There you are. So the extreme value theorem says if f is continuous on some closed interval, then f contains an absolute maximum and an absolute minimum on that closed interval. So what we're saying is that no matter, as long as we have a closed interval and a continuous function, right, we have an absolute min and max, no matter how you draw this, right, no matter what you do, oops, it's not the min, you dum-dum.
And those
right.
are
So it's not telling you how to find those things.
uh-huh.
It's not telling you what they are.
It
It just tells you that they have to happen. That's all it's saying. Now, what is the key piece for the extreme value theorem? Closed interval and continuous, right? So if you had this, there's no extrema here, no max, no min.
Yeah.
If you have this, not continuous, no absolute max, no absolute min, because you have the asymptote going on,
Uh-huh.
right? So that's all this is talking about, is just like when can you be guaranteed to have a biggest and smallest value on some closed interval? Or what do you need to have to be guaranteed a biggest and smallest value? You need to have a closed interval and a continuous function.
Yeah.
That's all we're basically saying. Is that okay?
Yeah, that makes sense.
Okay. And then you said mean value is the other one you wanted to talk about?
Yeah.
Sure. So let's go ahead and grab the theorem. Oops, where did you go? There. Okay. So what this is saying is that it says let f be a function that satisfies the following. So it's continuous on some closed interval. It's differentiable on the open interval, so everywhere but the endpoints.
Yep.
Then there is some other number on that open interval where the slope at that number is equal to the average of the slopes of the endpoints, or the average of the average slope for the curve, right? So like,
Oh.
let's say we have this, right? So this is just the slope for that line, right?
Yep.
So what the mean value theorem is saying is that there's some point on there that has the same slope, right? It's all it's saying.
Yeah.
Just that there exists something that has the same point, or has the same slope somewhere. Could be more than one point, right? On this one, it kind of looks like there's probably two. But that's all it's saying. So again, where can this fail?
When it's not continuous on a closed interval. It's not differentiable.
Yeah. So let's say that we had this as our f of x. Now it's continuous
Yeah.
on the closed interval, but it's not differentiable, right? Because if I look at this, the average slope is 0. Is there any place on here with slope 0? No, man, because what's the slope here? Yeah, it doesn't exist, right? So there's no place that satisfies the mean value theorem because we're not differentiable on the whole thing, right? The other place where we can get into trouble is if we're not continuous everywhere, right? So again, let's say we have this. Using the mean slope should be 0, but is there any place on here with the slope 0? Any point on here with slope 0? No, man. Right? Like, even if I'm like, oh, what about like right here? Well, it's still like,
Yeah.
kind of increasing a little bit. So that's kind of what we're saying with those things. For the most part, these are just like proving you use them to prove the existence of something. Now, how would Mr. Kulik ask a question about something like this, using a mean value theorem, extreme value theorem? Yeah, so it'd be like, okay, here's a situation. If I use the mean value theorem here, or somebody like Mr. Kulik used the mean value theorem and concluded this. However, it's not actually right. Why didn't it work? So again, it's like, it's good for the mean value theorem. It's either going to be we didn't have the continuity or we didn't have the differentiability. There's only two things that can go wrong, right? And for the extreme value theorem, there's again only two things that can go wrong. Either you're not continuous or you're not closed, right? So just trying to figure out which one of those two things we were missing. If I give you a problem like that, where it's like, yeah, I used the mean value theorem, but it wasn't right. Why didn't it work? You know, you're just trying to figure out like, okay, could be one of these two things. Which one of them is it?
Yeah.
That's all. And again, those would probably be like a 1 point kind of question, because it's like either you know it or you don't. You know, and there's really nothing to do there. John.
Between like squeeze theorem, intermediate value theorem, and so on, and median, which, I mean, I'm assuming you're gonna have some like solve with the squeeze theorem.
Yeah, like a
like,
squeeze theorem is a tool to value that you can use to evaluate a limit.
Besides the questions you described, do these ever come up in a way to solve a different problem? Like, do we ever really use these beyond just like saying, okay, we can do this because it exists?
Yeah, I'm trying to think. So the mean value theorem is one where you can like compute a specific value. So like I could use the mean value theorem to find the location on a curve that has that specific slope, right? So like if I need us, you know, if I have, you know, let's just say like we have f of x is equal to like x cubed minus 2x squared plus 6x minus 5 or something. And we're talking about on the interval from like, 0 to 2 or something. And we want to find, find x such that f prime of x is equal to like the mean value. So I would start by calculating that mean value. So that would equal like f of 2 minus f of 0 divided by 2 minus 0. So whatever that number is, I'm just going to call it c for right now. And then I set c equal to this. And then solve for x, right? And I could do that. Here I would probably use Newton's method or something to do that solving, because that's a cubic polynomial and I'm not really interested in trying to solve that algebraically. But that's an example of like using the mean value theorem. Like I know that this value exists because, again, continuous and certainly differentiable. So I know that this exists, and now I can be guaranteed to find it. That's kind of what you would do. But mostly these are like, they can be used to show something is possible. Squeeze theorem you can use to actually evaluate a limit, but the other ones are just like kind of showing something exists, showing something's possible. What else did you guys want to talk about? So I think on here, the highlighted ones were the ones that were in this, were in these set of problems that I did the video on. Aside from that very, very last one that we just did together. That one's going to be on this video. But that's what the highlights are on this list, are just ones that I did because I thought they were good ones to review, because they either touched on a lot of concepts or like closely resembled something I'd expect you to be able to do that was at like an appropriate level, like the related rates problem or the optimization problem. I think these are pretty good examples of something I'd expect you to be able to do. Where I don't think they were too hard or too esoteric or like the algebra got terrible or whatever. Blake, what's up?
So the max point value that you're going to assign to a question on this test is going to be 5, correct?
I think so, yeah. That sounds right. And the minimum point value is 1, and there's lots of stuff in between.
Yeah, so for those 5 point value questions, is that going to be like a related rates question where you have it so that one section is worth 1 point? So
I think that the multi-part, so these 50 multi-part problems I think there's 5 of them, and they all are worth 10 points. So they have like 10 points of stuff that you have to do.
Yeah.
I don't think any of them have a 5-point part to them.
Okay.
I think
Okay,
most,
but those equate to more than 5 points. Okay, like the multi-part question.
right, because most of them are like
Are-
more than one skill. Yeah. So like a 5-point problem might be just like do the derivative of this, and it's just like it's just going to take some time.
Okay.
You know,
Yeah.
and just because it's basically a time consumption
Uh-huh.
issue. So the stuff that should be quick is worth a little bit less, or the stuff that I ask you to do lots of things, or is super time consuming, is going to be worth more. You know what I mean?
Yeah.
But there's not a lot of 5-point things on here, to be honest with you. I tried to keep most things like 2 to 4, because I didn't want anything that was like terrifically time consuming. You know what I mean?
Yeah. So like the chapter 3, part 2, like those derivatives would probably be more like closer to 5.
Yeah.
Just like a gauge, I guess.
Yeah. Probably like,
Or related to this question.
yeah, so like I would say maybe a better gauge would be like like find the maximum minimum
Oh.
for something, or like find where just like, okay, so you have to do the derivative, so that's like a point. You have to solve the derivative equal to 0. You know, like that's maybe a point or 2, because depending on what the algebra looks like, maybe that's easy or maybe it's not. You know, like you have to also find the critical values, the place where the derivative fails to exist. So maybe there's one of those in there. So maybe that's another point. And then you have to like do your first or second derivative test on this to identify what they are, or your closed interval test, which means plugging stuff back in. So maybe there's a point to do that or whatever. So like that's something that you can add up to 5 points pretty quick, because there's kind of a lot of stuff to do. Versus something that's just like, this is kind of just a crappy, complicated derivative.
Okay.
Or maybe it's like a L'Hopital problem that just has like, you have to do L'Hopital like 3 or 4 times.
Yeah, that makes sense.
You know, like it just like this time consuming.
Exactly, yeah.
Yeah. Well, even it's not even that ugly most of the time, but it's just like
Like a lot.
time consuming. There's a lot to do,
Yeah.
right? Like you have to step through 3 or 4 derivatives or something.
Yeah.
It's just like, if you make one mistake, it
You're-
boogers the whole thing up,
Yeah.
you know?